This video is going to be a quick overview of functions. We'll start with relations. A relation is a mapping from one set to another set. The sets could contain any elements at all, but normally, of course, in math class, they're going to contain numbers. So we're going to be mapping from one set of numbers to another set of numbers. Now we need to be able to distinguish between these two sets, so we give them names. The first set is called the domain, and the second set is called the range. Here's an example of a relation in mapping notation. So on the left we have the domain, on the right we have the range, and what we do is we draw arrows saying what the relation is. So for example, maybe 5 maps to 5, 6 maps to 6, and 9 maps to 10. That would be an example of a relation. Now in this case we have a discrete relation because we have a finite number of elements in the domain and a finite number of elements in the range. And it's also one-to-one because each element in the domain is mapped to one element in the range. And because of this, this is actually a special case of a relation called a function. Now, we can show relations and functions in multiple ways. This is just one way. So let's take a look at the exact same relation in a different format. Here now we have the exact same relation in green in a set of ordered pairs format. The first element in each ordered pair is a domain element, and the second is a range element. So this first ordered pair says that 5 in the domain maps to 5 in the range. That's this right here. The second one says that 6 in the domain maps to 6 in the range. That's this one here. And this third ordered pair says that 9 in the domain maps to 10 in the range. So it's just another way of expressing the exact same relation. Now, because we can express relations with ordered pairs, we can also plot those ordered pairs to express a relation on a graph. Here now, we have that the horizontal axis, usually referred to as the x-axis, is the domain. So we can see again that we have a 5, a 6, and a 9 in our domain. And then the vertical axis, usually referred to as the y-axis, becomes our range. And we can see that we have a 10, a 6, and a 5 in our range. Now in this specific example, it would be difficult, not impossible, but a little difficult to express the relation in terms of an equation. And so we would normally satisfy ourselves with one of these three expressions of the relation right here. But, as you well know, we can use equations to express graphs, and graphs map back to equations. So there is, of course, a fourth way to express a relation, and that's with an equation, which brings a whole bunch of powerful mathematical machinery along with it. So let's do another example of that. So here now we have a new relation. This relates all the elements of the set in X to elements in the set of Y. And we don't know necessarily what the elements of the set are without being told. Now we'll normally assume, if we're not told, that it's going to be all possible legitimate numbers, but it's nice to actually be told. So here we're told that X is in, or is contained in, the real numbers. This capital R stands for the set of real numbers. In other words, all the numbers that we use on a regular basis. The set of real numbers includes 0, it includes 5, it includes -2, it includes 3/4, it includes -0.3 repeating, it includes pi, it includes √2, it includes all sorts of numbers. The only thing that it doesn't include is imaginary numbers and complex numbers. So this part right here says, look, all the elements of this set are defined by this relation. And so we know that if we put a real number here, multiply it by 0.2 and add 1, we'll get another real number over here for y. And based on our understanding of linear relations, we in fact know that if we were to graph this, we would have a y-intercept of 1, and we'd have a slope of 1/5, because 0.2 equals 1 over 5. And so we'd be going up 1 over 5, up 1 over 5, and we could graph this relation like that. Here now, y again is the range, x is the domain, and we can see that our range is now going to consist of all real numbers. The range is all real numbers because all the real numbers will get hit at some point for some real number x being substituted into that expression on the right-hand side of the equation. So here we actually have a domain of all real numbers and a range of all real numbers. By the way, just in case you forgot how to convert 0.2 to 1/5, you notice that this is the tenths place. So 0.2 is equal to 2 tenths, and then you reduce by dividing numerator and denominator both by 2. So we have now that we can express relations in many different ways. Mappings, like in those ovals that I showed at the beginning, a set of ordered pairs, graphs, or equations. Now here are 8 relations, 8 perfectly good relations. 4 on the left are in blue, 4 on the right are in green. And there's something similar among all of the relations in blue that is different from all of the relations in green, other than the color. Pause the video here and see if you can figure out what that difference is. What distinguishes the relations on the left from the relations on the right? The key distinction is that on the right, every single element of the domain maps to a single element of the range. Whereas on the left, each of those relations has at least one element of the domain that maps to more than one element of the range. Let's take a look relation by relation. In the first one, I have the element 3 maps to both 2 and 5. That's an element of the domain that maps to 2 different elements of the range. In the second one, I have 1, 2, and 1, 5. Again, I have an element of the domain that maps to 2 different elements of the range. Now, actually, in both of these examples, I have this happening twice. I also have 4 maps to both 1 and 2, and I have 3 maps to both 2 and 5. But the key point isn't that it happens twice. The key point is that there's at least one element of the domain that maps to more than one element of the range. Okay, what else? Well, in the third one, we can see here's the one element in the domain that maps to more than one element in the range. And in the fourth one, there's many, many elements in the domain. Let's just pick this one right here that maps to more than one element in the range. It maps to this and this, right? So it maps to whatever this height is right here and whatever this height is right here. This element in the domain on the x-axis corresponds to some element in the range here and some other element in the range here. Now, each of these blue examples, because they have at least one element of the domain that maps to more than one element of the range, these are not functions. By definition, a function is a relation where each and every element of the domain maps to one element of the range. Okay, so now if we look at the green ones, all of these are functions. Let's look at them one by one. The first function here, we have 3 maps to 6, 2 maps to 5, 4 maps to 1, 7 maps to 2. Fine. Every single element of the domain maps to one element of the range. Let's look at the next one. 1 maps to 2, 3 maps to 5, 2 maps to 2, 4 maps to 5. Again, each element of the domain maps to one element of the range. It's okay that two different elements of the domain may map to the same element of the range. 1 maps to 2 and 2 also maps to 2. That's fine. The problem is we don't want one to split and to map to two different things. So this is also a function. Let's look at the third one. 1 maps to 3, 2 maps to 5, 3 maps to 7, and 6 also maps to 7. That's fine. It's okay for two different elements of the domain to map to the same element of the range. No problem there. The problem comes when one element of the domain maps to more than one element of the range. And here, if I look, for every single element of the domain, let's pick this element here, I get a specific element of the range. For this element of the domain here, I get a specific element of the range. For this element of the domain, I get a specific element of the range. For this element of the domain, a specific element of the range. So this one is also a function. Now, popularly, we have what's called the vertical line test, where if we have a graph, we can tell if something's a function by taking a vertical line and passing that line across our function and checking to make sure at every single place that we have a vertical line, it only crosses through the function once, or the relation, I should say. And if that is true, like I'm demonstrating it is true here with this parabola, then we know we have a function. And if we wanted, we could take this mapping right here and plot it out. 1, 3, 2, 5, 3, 7, 6, 7. And go through with a vertical line. 1, 1, 1, 1. It passes the vertical line test, and so it's a function. And we could do the same with the first two. If, on the other hand, we look at the blue ones, every single one of those fails the vertical line test. Here, in the circle, is one place where it fails. It only has to fail once to not be a function, and it fails right there. But it also fails here, and here, and here, and here. It fails all over the place. There are many elements of the domain for which there are two elements of the range associated. The third example here, same thing. I can take a plot here, 1, 2, 2, 7, 9, and 3. Well, it passes the vertical line test right here, but it certainly fails there because that line goes through the graph 3 times, all in one vertical line, which is a failure of the vertical line test. And we could plot out the first two sets there and also see that they fail the vertical line test. So the relations on the left are not functions. The relations are on the right are functions. In words, we say that a function is a relation where every element or member of the domain, every single one, maps to one element of the range, but not more. In other words, a function is a one-to-one mapping, that is, every element of the domain maps to one element of the range, or a many-to-one mapping, that is, you could have more than one element of the domain mapping to the same element of the range, but not a one-to-many mapping. One-to-many mapping means you have one element of the domain mapping to many elements of the range. That's not allowed for a function. We can think of a function as kind of like a machine that transforms each input into a specific output. So every time that machine receives a specific input, say a 5, it will always transform that 5 into a specific output. You could supply the machine with a 5, it will always transform it to some specific output, say a 25. If you supply the machine a different input, well, then it can transform it into some other output, but it will always treat like or identical numbers the same. So if it's a 5, it will always treat it the same way. If it's a 3, it will always treat it the same way. That's the idea behind a function. And with that, you now have the background you need to do exercise 2A.